Let's start once again with a probability and statistics application. We are after a probability density function, PDF, f of x. It's a little bit more complicated than the ones we've done so far. We've done exponential decay, normal curve, which did have some complication to it as well. This time, let's have an exponential decay, but let's multiply the exponential decay by a power function, which grows c times x times e to the negative lambda x, where c and lambda are positive constants. And the domain I'm thinking about is also values of x that are positive. I'd like to see, can I use this as a probability density function for statistics applications? In other words, does the integral of this equal 1? I hope it feels intuitive that probably not, as is. C and lambda probably can't be just any old thing that you want them to be, and the integral still be 1. But maybe some choices of c and lambda give you an integral equal to 1. And since it's over all positive values of x, that means I want the integral from 0 to infinity to be 1. The graph of this kind of function goes up pretty rapidly at first because of the c times x term, that factor there. But then it decays to 0 pretty rapidly in the end because of the exponential decay there. Can I choose c and lambda? Can I choose c and lambda so that the improper integral of this function from 0 to infinity not only converges, but also equals 1? I'd like to try to answer that question here. So let's do the calculation as we've always done it, and as you should continue doing it, including on a test if necessary. It's improper because the upper limit of the integral is infinity. Remember that it can also be improper when your function happens to have a vertical asymptote on the interval of integration, but in this case, it's because of the infinity. Assuming the limit exists, I can factor out the c, and I can also factor out the c in front of the limit sign that defines the improper integral. I can write it like this. I'm implicitly assuming this improper integral is going to converge when I write this, though even if it diverged, we've typically still written this kind of thing, but just in the end, we say the answer is infinity, so we say the integral diverges. To do this integral, I hope you've got enough experience now to know that integration by parts is the way to go. V prime should be something easy to integrate. Both of these factors are easy to integrate, so we could choose either one. However, if we choose u to be x, which is the best thing to choose here, that does make u prime simpler. Therefore, v prime should be the other factor, e to the negative lambda x. And v is going to be the integral of that, will be negative 1 over lambda, e to the negative lambda x. So it's a little tricky in finding v, but you should be at the point where you can do this pretty quickly. Using the integration by parts, I'm going to get c times the limit as b goes to infinity of, careful, be really careful, u times v, product of these two things, will give me a negative x over lambda, e to the negative lambda x. Evaluate from 0 to b. With integration by parts, there's no need to change the limits of integration. That's only with substitution. Minus the integral of v times u prime, the product of these two things. The negative 1 over lambda can be factored out in front like this. And you end up integrating e to the negative lambda x. 2 minus signs make a plus sign. Now plug in the numbers before taking the limit. Lots of letters. What's getting plugged in for? You're plugging in for x. think of C and the lambda as constants. And of course, E is the number E. That's constant too. If I plug in x equals b, I get negative b over lambda e to the negative lambda b. If I plug in x equals 0 into this one, it goes away, not because e to the 0 is 0. It's not. E to the 0 is 1. But because you'd plug in a 0 there. That's why you would get 0 when you plug in 0. I'll emphasize that by saying subtract negative 0. I didn't have to write that. For this integral, we're going to get another factor of negative 1 over lambda. So we'll get a negative 1 over lambda squared e to the negative lambda x. And let's use parentheses to emphasize we're going to evaluate that x going from 0 to b. I probably should have written an x over here as well. X goes from 0 to b, since there's so many letters. Keep plugging in. We're almost ready to take the limit. I'll write this one like this. And then minus, plug in x equals b, I'll get a 1 over lambda squared, e to the negative lambda b. Plug in x equals 0, I'll get minus 1 over lambda squared, e to the 0. E to the 0 power is 1. Am I ready to take the limit as v goes to infinity? Yes, I am. That term right there is a constant times exponential decay. Lambda is positive. It is important to remember lambda is positive here. So negative lambda is negative, and negative lambda times b, because b is going to infinity, is negative. E to a very large negative number gets closer and closer to 0 as that negative number gets larger and larger. It does go to 0 as b goes to infinity. What about this one, though? You've got an exponential decay, e to the negative lambda b, but you also have a growth factor, b, as b gets large. I hope you have enough experience by now to realize a polynomial growth times an exponential decay, the exponential decay is going to win out. This product is still going to go to 0. Is there a way that can be proved? Yeah. We could use L'Hopital's rule. And I think it's worth using L'Hopital's rule once more in your life, or you see me do it once more in your life, to remind you what it is. This is, you could call it an infinity times 0 indeterminate form. You can't apply L'Hopital's rule directly to that, but if you modify it a little bit by writing e to the negative lambda b as 1 over e to the positive lambda b, then it becomes an infinity over infinity indeterminate form. And you can apply L'Hopital's rule to that directly. By taking derivatives, not the quotient rule, right? L'Hopital's rule is not the quotient rule. We're not taking the derivative of this entire fraction. We take the derivative of the top and the bottom individually and make a new fraction with those derivatives with respect to b. That's L'Hopital right there. Assuming this limit exists, if it does exist, these will be equal. And that limit no longer needs L'Hopital's rule. And remember, in general, if you try to apply L'Hopital's rule when it cannot be used, you can get the wrong answer. It would happen to be the right answer in this case, but just think about it. You've got a constant divided by something growing very large. The fraction is growing very small. This limit is 0. So that means all this becomes c times 0 minus 0 plus 1 over lambda squared times 1 c over lambda squared. Assuming both c and lambda are positive, lambda being positive means it's not 0, so I'm not dividing by 0. The integral converges when lambda is positive to this, c over lambda squared, which is not 1. But if I set it equal to 1, it gives me a condition under which the original function is a probability density function. 1 meaning all the probability, 100%. A probability of 1 or 100% that some value of x that's positive will happen when you perform your experiment for which this is a model. Something's got to happen. I'm not trying to solve that equation. I'm trying to rewrite it in a simpler form. I mean, I guess you could say I'm solving that for c in terms of lambda. But what this is really giving me is a relationship between c and lambda that must be true in order for the original function to be a PDF. And that means I can now go back to the original function, f of x, and replace c with lambda squared. F of x equals lambda squared times x times e to the negative lambda x for x positive is a PDF, no matter what lambda is, as long as it's positive. For any fixed positive value of lambda, that will be a probability density function. Mathematica, please confirm this for us. So I integrate from 0 to infinity of lambda squared times x times e to the negative lambda x. I make a lambda, by the way, by doing escape L escape. Lambda starts with an L, that's why. What will Mathematica say? It says we're right, though it does give the condition that for real lambda, lambda has to be positive as part of its answer. Well, at least it did in the last class. Oh, I know why. I need to clear the value of lambda. Let me do an arbitrary value of lambda. Then it thinks a little longer, but it does say 1. If RE of lambda is positive, that means what's called the real part of lambda is positive. Mathematica is assuming lambda might even be a complex number, like 2 plus 7i or something, where I squared is negative 1. As long as the real part without the I is positive, the integral will converge. When lambda is a real number, RE of lambda being positive means lambda itself is positive because it's a real number. RE stands for real part. Anyway, this is now a probability density function. To whet your appetite for our use of these things a lot at the end of chapter 8, which will come after spring break, I'd like to do some simulation with this to help you understand what it means. This PDF does happen to actually have a name. It's called a gamma distribution. In general, the gamma distribution has 2 parameters, 2 constants. They're called alpha and beta. To make this work, I take the alpha equal to 2 and the beta equal to 1 over lambda. If I enter this, we shall get the same formula. Yes, right here. Lambda squared times x times e to the negative lambda x. That matches when x is positive. 0 true, what does that mean? Well, don't worry about it. That's effectively saying this is 0 when otherwise, when x is less than or equal to 0. I don't know why Mathematica puts true there. It seems a little silly to me to put true there, but it is. This is our PDF. If you use a built-in command called RandomVariate with a capital R and a capital V, we can simulate sampling from this distribution, effectively come up with simulated data values that follow this distribution. I'm going to use RandomVariate to do that, and I'm going to store the numbers that I get, the data, in a variable that I'm going to call data. Effectively, and now I'm going to take lambda equal to 1/2, a particular number. I'm going to just copy and paste this gamma distribution right here, then put a comma, then 100. That's going to generate 100 data values. All at once from this distribution. What does this mean? How can this be related to probabilities? It's helpful to plot the PDF as well as the numbers themselves, the data values. Plot will plot the distribution itself, say x going from 0 to 20. There's the distribution itself. That's similar to the one I drew by hand. To plot the numbers themselves, the data values, inside this show, which combines different graphics into one picture, use NumberLinePlot data. And an extra condition needs to be here, a comma, spacings, arrow, 0 will plot the data values on the horizontal axis. Here we go. There they are. Notice that, for example, about, well, 8 is right there. 1, 2, 3, 4, 5, 6 data points are between 8 and 10, for example. 6 out of 100, 6%. I wonder what the integral of this PDF is from 8 to 10. Again, lambda is 1/2 here. Lambda squared times x times e to the negative lambda x. From 8 to 10, get a numerical approximation. 0.05. 5%. Close to 6%. We got 6 out of 10 data points. Look where the cursor is. 1, 2, 3, 4, 5, 6. Being between 8 and 10. 6%. 5% of the total area is between 8 and 10. The probability that your experiment is going to generate a data value between 8 and 10 is about 0.05. And hey, 6 out of 100, 6%, is very close to 5%. If I do a different simulation, if I redo the RandomVariate here, I'll get different numbers. And this plot will look different, but hopefully there will still be close to 5 data values between 8 and 10. So these are different now. And yeah, it's 1, 2, 3, 4, 5 of them between 8 and 10 this time. Very closely matching this 5%. That is one way to interpret the meaning of this distribution. Does a gamma distribution have applications? Yes, plenty of applications. The exponential distributions that we looked at last week are a special case of the gamma distribution. That's one application. And exponential distributions, I mentioned, are widely used to model waiting times, like until the next earthquake, I mentioned. It also, another special case of the gamma distribution is called the chi-squared distribution. Lots of applications of that in statistics. More generally, anytime you have a function whose graph looks like this and who you think could model a data set, a gamma distribution is a good thing to try. It's called a probability density function for a reason. It's because the data are densest near the peak and less dense the lower the function is. And that's true no matter how big my data set is, 100 data values or 1,000 even. They'll be denser where the PDF has a higher value. The probability is denser, so to speak, near such values of x. And there'll be fewer data points where the PDF is lower, less dense. Okay, so this is applied to statistics, but it can be applied to physical thin rods, for example, and their masses. Okay, the ideas are analogous. Feels less phony applying it to statistics, I think. Would you have to show all these details, including L'Hopital's rule on the homework? Probably not. Not L'Hopital's rule. I mean, you could just intuitively say that it's going to go to 0 as b goes to infinity. You do want to be sure you're right, so you would perhaps want to plug in large values of b and see if the outputs are small if you pick a particular value of lambda.